Hello, I'm Rebecca Lewington. Welcome to our podcast. I'm here with Melissa Uribe, who's particularly focused on a newish technology called FUSA, functional safety, which is a critical enabling technology for autonomous vehicles. More than 1 million people are killed every year in automobile accidents, and we'd really like that number to go down when we take humans out of the loop. She also represents Micron on the Automotive Electronics Council, which establishes common part qualification and quality system standards. So, Melissa, thanks so much for joining me.
Well, thanks for having me.
So first, tell us a bit about yourself. What's your background and what's your current role?
So I started out in Micron in 2010. I was part of the Mnemonics acquisition. And when I came in, I was quality and reliability manager for embedded and automotive. So I've been in automotive quite a while now. So I've always had kind of that quality and reliability focus. But more recently, I've moved over in 2019 into functional safety.
Excellent. Now, something you told me that I should ask you is, what's the difference between quality and safety? Because I'm sure most people like me think they're kind of the same thing.
Sure. I think that's a common misconception. Quality and safety do have some commonalities. For safety, you do want a low failure rate. That's pretty critical as well. But really, they're not the same. Quality is really the measure of a failure in time. So the amount of failures, a failure rate. Where safety is more the predictability of failures. So your goal is to reduce the risk from failures. In a way, with safety, you kind of accept that there are going to be failures. That's just a foregone conclusion that there will be failures. But what you want to do is understand what those failures are and figure out how to manage them so that you can keep the car and the people out of harm.
Right. And so going on from that, what's functional safety? It's one of those terms where I know what functional means and I know what safety means, but I'm putting them together and they don't mean anything anymore.
Right. So functional safety is really the absence of unacceptable risk.
And unacceptable risks.
Unacceptable risk. Yeah. And those are, in this case, from electronic systems in the car.
Okay. Can you say a bit more about this? I gather there's two different types of fault. There's systematic errors and random hardware faults.
Exactly. There are two different classifications of faults. So we have systematic and random hardware faults. The systematic faults are really more things like you would think of an error in the design or the firmware. Mm-hmm. And so for systematic faults, they really can affect every component, just depending on if you're in the situation that brings out that failure. So really, to address a systematic fault, you really have to look back to your development process and make sure that you are following best practices for the design, the verification, simulation, validation of your product to make sure that you can minimize or eliminate those systematic errors. The other classification of faults is random hardware faults, and that's more my specialty. These are more like defects. So these are those little faults that appear at random over the lifetime of the product. And so for random hardware faults, what you really have to do is figure out how to manage those failures. So we look to incorporate things like safety mechanisms in order to detect the failures.
Which leads me to my next question. That's another somewhat opaque term. What's a safety mechanism in this context?
Right. A safety mechanism is essentially a feature that is built into the product that allows you to do sort of an introspection. So to really look for faults that are happening inside the part as you're operating. So it allows us to detect the fault and then alert the system that something is wrong. And so there's really some key elements to having this type of safety mechanism. The first is it has to be able to detect a fault. The second is it has to alert the system. And the third is that it has to alert quickly enough that the system can react before there is harm.
Before it enters an unacceptable state.
Exactly, the unacceptable risk. Right.
Yeah, go on.
Well, so I was going to say there are a few examples that you can see in some standard products today that are kind of like a safety mechanism. You can see alert flags in storage products that come back in the response protocol. And you can see things like ECC write link registers in things like the LP DDR5. So these are standard features that are alerting the customer, the host system, that there is a problem with the device.
I get it. So yeah, basically no surprises. You don't want anything. You don't. And the important thing is that the system is able to introspect to know when it's going wrong for itself.
Exactly.
So let's jump back to managing random hardware failures. How do you do that?
Well, really, what you want to do is start by understanding what those hardware failures could be. So we really start with understanding the base failure rate of our product, and then determine what safety mechanisms we could use to detect those faults. A fault that is detected and alerted to the system no longer poses that safety risk. Any fault that is undetected then becomes a residual failure rate, so a leftover failure. So really, to determine that failure rate, we do an in-depth analysis of our product using a process called failure mode, effects, and diagnostic analysis. We analyze the faults of every functional block in the device, figure out what the failure rate is for those faults, and then overlay our effectiveness of the safety mechanisms to figure out if we can detect the failures and how many we can detect. The process is really part of a standard for functional safety called the ISO 26262. Yeah.
Now, I read one of your papers. You're going very, very deeply into the design of the chip. You're pretty much going down to the silicon level to assign risk to every single piece of that and add them all together and figure out exactly what's going on.
You are. It's a pretty in-depth process.
Right. That's really interesting. Now, when you add all this together, I gather we're trying to meet another standard called ASIL D, which sounds like
we
something from Lord of the Rings. What is that?
So we refer to ASIL. ASIL is part of the 26262 document. It's the it's an automotive safety integrity level. And ASIL really refers to the level that you're able to meet with your product. So there are a few different elements to that. There are requirements based on the systematic side. So in other words, what amount of or type of development process you're going to go through. So the specific requirements are more stringent as you get to a more challenging ASIL level. And also you have to meet certain requirements then for the random hardware side that relate to the failure rates. So for an ASIL D, which is the most stringent in the 26262, that is 10 failures in 1 billion hours. And that's for the system. We are just a memory component in the system, so we don't get that whole allocation of failures.
Wow. So this translates to memory and storage things that really, to several significant figures, never fail in an unpredictable and unacceptable manner.
Right, exactly. They can fail, but they never fail in a way that's undetectable. Mm-hmm.
Wow.
Right, that's our goal.
So what products is this going to be built into, and what innovations were necessary to make it work?
Right. Well, so our first product that we're building this into is an LP5. And so that
LP5?
product, LPDDR5, sorry. Low product DDR. Mm-hmm. Right. Exactly. That's our first product that this is being built into. But there are other products, memory products in our portfolio, including storage products that we will continue to develop as well. Right.
And the LP's low power DRAM is an increasingly big player in the automotive space, I gather, going forward.
It is. So yes, that is why our focus has started on low power DDR5.
Okay, what else has to be done to make this work at a system level?
Right. Well, besides working on our safety features that would allow us to work within the existing JEDEC protocol, we also have to work to enable the ecosystem. So working with our customers and chipset vendors to make sure that they enable the use of those features so that they can be used in safety systems.
Got it. So it's really a team effort. Mm-hmm. So next question, how new is this idea? How new is functional safety? When, to put it another way, how do people try and achieve the same level of safety today?
Right. So historically, in order to achieve functional safety with memory devices, I don't think the memory devices were very well understood in the automotive safety applications. So the early approach was really more of a brute force method, honestly. It was more to build in redundant memory subsystems. So by doing this, you could have two memory subsystems, one that would run the application, and the other was kind of like a double check. So in a way, like the safety mechanism for the first one. And so if the two memory subsystems provided the same response, then you could expect that those systems were running cleanly and you could trust the results. Of course, that assumed, that defects are random and wouldn't hit both at the same time in the same way. But if your memory subsystems then provided you different results, you knew that something was wrong and you could move to a safe state, which would be something like pulling the car over to the side of the road or turning off the system and allowing the driver to take over, something like that. But honestly, the tough part about the memory subsystems, about having dual memory subsystems, is that you also have to consider the systematic faults. And so if you design two memory subsystems with identical components, they can fail in the same way. And they, in theory, would be under the same circumstance at the same time. So that may not be sufficient to cover systematic faults. And in that case, you may need to build separate memory subsystems that have different designs, maybe even different suppliers.
And now we're sounding like the way you build systems for space exploration, and that right. Doesn't sound like it's very well, not very economically viable, or really very functional for something you're trying to build into millions and millions of vehicles.
Right.
So your approach is cheaper, faster, better. It's sounding pretty good.
It is. Yeah, it allows us. So we're addressing those systematic errors. We are building in alarms. And so instead of building a system with, dual memory subsystems, you can just build the one memory subsystem. And so it's definitely cheaper than having that redundancy. We also provide safety documentation that assist our customers, the integrators, with building our parts into their system. And the system bandwidth can even be improved when the errors are detected closer to the point of failure, rather than relying on waiting for them to propagate further into the system.
Right. Which leads me to my next question, which is the downstream impact. Now you've got functionally safe memory, and in the future, functionally safe other things. What does that enable?
Right. Really, this enables the autonomy concept for autonomous driving cars, maybe assisted driver assistance cars as well. So it builds in those advanced driver assistance systems. These systems, in theory, can help with congestion, maybe improved efficiency, less stress to the driver, and like you said earlier, fewer fatalities. I've even heard maybe fewer emissions from that as well.
Oh. Right.
Yeah. So I really think full autonomy, it can't happen without a dedicated functional safety approach. Right.
So Melissa, if you don't get this right, it's going to be your fault if we're not don't have self-driving cars. So switching gears a bit, I wanted to ask you about what you do as you represent Micron on the Automotive Electronics Council. What does that entail? I don't know why you're laughing, but I'm sure you'll tell me.
So it actually isn't really related to safety at all, but yes, I am our Micron rep for Automotive Electronics Council, which is the governing board for developing qualification standards for integrated circuits, electronic devices, components that are used in cars. So on that board, we are technical members. So Micron, influences what's in the standards and helps to define those standards and continue the growth of those standards as the technology changes. So I contribute directly to that. Today, we actually have 3 different standards that are active that we're involved in from Micron. The Integrated Circuit Qualification Standard, which is Q100, the multi-chip module version, which is Q104, and a new board level reliability standard that we're working on as well.
I love it. You live in a world of standards and acronyms. It's amazing. So yes. Just to finish off, what's next for Micron and functional safety, and what's next for you?
Right. So for Micron and functional safety, we're continuing to expand our portfolio. So pushing those functional safety efforts into more products and continuing to drive the systematic processes and process certification with our third-party consultant and product certifications with our third-party consultant. So that will allow us to validate capabilities and to continue to put out new products that are capable of being used in systems up to ASIL D.
Excellent. And you?
Well, for me, I'm having a great time with functional safety. So I really enjoy it. And I'm hoping to continue to take the learnings from the random hardware analysis that I'm doing to improve future products and maybe help identify additional features that we can build into those products. There's a lot going on and it's a lot of work, but it's a lot of fun.
Excellent. Well, thank you so much for this. It's really fascinating to get a peek under the hood, sorry, pun intended, of a critical enabling piece of the automotive ecosystem going forward. So again, thanks very much for your time.
Thank you.